Welcome to this detailed explanation of how to calculate volatility and drift using Markov chain methods. We'll cover the mathematical framework, estimation procedures, and validation techniques. Let's start with the mathematical framework. The foundation of our analysis is the stochastic differential equation, or SDE, that describes asset price movements. ds over s equals mu dt plus sigma dw here. S is the asset price, mu is the drift parameter, sigma is the volatility parameter, and dw represents a Wiener process. To estimate these parameters using Markov chain methods, we first need to discretize our continuous time model into discrete time steps. This gives us delta s over s equals mu delta t plus sigma times epsilon root delta t, where epsilon is a standard normal random variable. For practical implementation, we typically work with log returns. R underscore t equals ln of s underscore e over s underscore t1. These returns are approximately normally distributed under our model assumptions. Now, let's define our Markov chain state space. We'll discretize the returns into k-states, typically using quantiles of the empirical distribution. Here's a visualization of how we might divide the return space into states. The key to our Markov chain approach is the transition probability matrix P. Each element P underscore ij represents the probability of moving from state I to state j in one time step. We estimate these probabilities from historical data by counting transitions between states. Now, let's look at how we estimate volatility. The volatility sigma can be estimated from the transition matrix using sigma squared equals the sum of p underscore j times r underscore j minus r underscore I squared over delta t, where r underscore I and r underscore j are the central values of states I and j. Similarly, we can estimate the drift parameter mu using mu equals the sum of p underscore j times r underscore j minus r underscore I over delta t. This gives us the average rate of return implied by the transition probabilities. Let's discuss validation techniques. We can validate our estimates using 1. Bootstrap resampling to assess parameter stability. 2. Comparing simulated paths with historical data. 3. Testing the normality of standardized residuals. Let's work through a simple example. Suppose we have daily returns data that we've classified into 4 states. After counting transitions, we get this transition matrix. Using these values and our formulas, we can calculate 1. The volatility estimate by summing the squared differences. 2. The drift estimate by summing the weighted transitions. This gives us estimated annual volatility equals 25.3%, estimated annual drift equals 8.7%. In conclusion, the Markov chain method provides a robust framework for estimating volatility and drift parameters. It's particularly useful when dealing with non-normal returns or regime switching behavior. Remember to validate your estimates and consider the stability of your results across different state space definitions.